And there we are. We're live with this session. The speaker of today that I'm very happy to present to you is Peter Lowry. I have been, I know Peter for a long time, but we don't meet that often because of each other's. We typically meet at conferences, but Peter is the CEO of Chronicle Software, which is a firm specializing in low latency software and especially for trading firms, both in Java and C++. So he's very good at performance and especially on the JVM. But that is really just the shallow story about Peter because he has a very popular blog on at vanillajava.github.io, and is speaking about a large number of things, like especially related to performance, or even the latest blog entries were about quirks that you can find in Java. They are all very interesting and advanced to read. So please go and check out this blog. Is wonderful. And the other thing that I remembered but I forgot, but then today I actually rediscovered, was that he's really a superstar on Stack Overflow. He has like 13K answers on Java topics. He has a total amount of the Stack Overflow score is like 520K, which is incredible to me, and is among the top 0.01% of all the people on Stack Overflow. So if you want to find like a real expert, well, Peter is one of them. So a little bit of trivial. Peter is Australian, is from Melbourne originally, but he's now been living in London for 20 years. Actually, London, UK, I should say. Um, for about 20 years now. So I think he's working there, most customers and probably all around the world. But so this session is about how your allocation rate could be hurting vertical scalability. And having said that, Peter, the stage is yours.
Yes. I'll probably add just one little thing that I'm quite pleased about is that for File IO badge on Stack Overflow, I'm the only gold holder in any language.
Yeah, well,
So
I didn't mention the number of badges that you have because there are just too many, but it's like about 2,000 among the gold, silver, and bronze. But yeah, I mean, that's the caliber of the person that is presenting the session today. It's all yours.
yeah. All right. So the topic today is about considering how allocations impact your system. And in particular, it's shifting your mindset from not just looking at things like the GC pauses, which are monitored and can be quite lengthy, to also thinking about the impact of the allocations that triggered that GC pause. There's a general wisdom that allocations are very cheap, and certainly they're cheaper than they used to be. However, what you can find is that as you try to use more and more CPUs, more and more threads within a system, particularly systems with a high core count, your allocations can become a bottleneck. And those allocations can far exceed the cost of the GC, particularly if it's very short-lived objects, which is the case in both the benchmarks I'm looking at today. So in particular, for very short-lived objects, the cost of allocating those objects when you're trying to use all your threads can exceed the cost of cleaning them up by nearly 2 orders of magnitude. So that's often an underrated consideration is if you want to make use of the whole system, allocations can potentially be hurting you. So I'm going to look at that in a bit more detail. Now, so why is there a general wisdom that allocations are relatively cheap? Well, the thing is, if you look at a relatively small number of threads, and in the past, um, uh, there wasn't that long ago. I remember when computers only had 4 cores. So 4 cores uh, is not as large as it used to be. Now we're looking at machines with far more than 4 cores in them. even desktops and laptops with far more, or even phones with more than 4 cores. Um, and but if you look at for a small number of threads or being active, the amount of time it takes to allocate an object is both pretty flat and fairly cheap. So in particular, at around for a small object of 44 bytes, we're looking at around 20 nanoseconds, which is no big deal. 20 nanoseconds, and you can have like 6 threads allocating these objects very quickly, and you don't get into any kind of scalability issues. Where you do start to see scalability issues is for medium to larger objects, but again, it's still not too surprising. If you've got a lot of threads creating large objects, you kind of expect that that's going to have quite a bit of overhead, and obviously you've got to do something with those objects. So just creating them isn't something you're going to be doing for long periods of time. However, if we zoom back a bit and look at, well, what happens when you have 32 threads? Well, you can see that in each case, even for the smallest objects, the latency just ramps up. The latency increases pretty much linearly with the number of threads, as it does for the larger objects, but even for the smallest objects, the more threads you have trying to allocate objects, the longer it takes to make those allocations. So that even for the smallest objects, you're looking at about 150 nanoseconds. For still a medium-sized object of about 100 bytes, you're looking at about 250 nanoseconds. So where does this matter? And also, how can we see that this is some sort of threshold being reached or saturated, resource being saturated? Well, if we invert this around and look at what is the allocation rate in terms of gigabytes per second we're achieving with the different object sizes, you can see that as the number of threads trying to create those objects goes up, it quickly reaches a maximum in terms of the number of gigabytes per second it can allocate, and in many cases it starts to tail off a bit. This is not too surprising because this is the machine has only got 16 cores. It's got 32 logical CPUs, but it's only got 16 cores. So once you go beyond 16, you really are um, not necessarily going to get much improvement, and you may actually get more the overhead of trying to use all of those logical threads may slow things down a little bit. Um, but you can see quite quickly that somewhere between 4 and 6 CPUs, you're able to allocate as much as you can, as you ever will be, and having more threads on the system doesn't actually increase your allocation rate. Um, and the reason this is particularly important is that uh, uh, that um, that you just don't get that if you have a lot of allocations, if you're spending a lot of time allocating objects, you can find that adding more threads or more CPUs or trying to use more CPUs in the system won't actually help. Now let's look a little bit at the architecture of a typical CPU. This is an older one, but they're arranged very similar to this in that you've got a primary L1 caches sitting in the middle. Each L1 and L2 cache is local to that core. So if your threads microservices can stay within the L1 and L2 caches, you get very good scalability because they're not having to go to any shared resource or any contended resource. So they're working completely independently at that point. However, by the time you drop down to your L3 cache, there is a little bit of concurrency in terms of how the L3 cache can behave, but it is a contended resource. So if you're hitting your L3 cache, you're already compromising on scalability. And in particular, if you're going exceeding your L3 caches, as you are if you're allocating objects really quickly, then you're going to the memory bus, and then it's a heavily contended resource. Again, you get a little bit of scalability, but in reality, you're going to max out the rate at which you can push data out to your memory banks. What we also found is that if you go to multiple sockets, a second socket can help, but it doesn't. A second socket doesn't give you twice the throughput. It may give you 50%, 60% improvement, but having more sockets with more memory banks does have an improvement, but it's not entirely linear. So let's look at a more realistic example. So in the first benchmark, all I'm doing is just creating objects as quickly as I can. They're all very short-lived. I'm not doing anything with them really, other than just making sure that they don't get optimized away to nothing. So that there's something to benchmark. So let's look at a slightly more realistic benchmark. So in this benchmark, I'm sending multiple objects. This is from the test framework, where you can describe your data in YAML, and then it does data-driven tests. So you can see you can get quite a bit of information here. This is a 44-byte object, and that was where that 44 bytes came from in the previous benchmark. Um, and we can see that with 44-byte objects, how does the system behave? And here's a couple of examples. Um, so in this case, what I'm doing is I have multiple TCP clients that are talking to, each one's talking to an echo service. The echo service is trivial. All it does is whatever message you send it, it sends back. Um, Now, one of the things that it's important in our framework is to minimize object creation. And we do this for reducing jitter and increasing throughput, but it also is for improving scalability. And um, part of the point of this talk is showing, well, how much difference does it make to reduce your object allocations in terms of scalability. So what this microservice is doing is that it will optionally, based on a system property, create a copy of this one 44-byte object or not. So what is the difference between creating a copy or not creating a copy um, before sending it? So in this case, it's for every message. So this is including all the I/O over TCP over loopback. Um, and how much difference to the performance does it make if I create just one object for each message I handle? Um, and generally, you might think, well, in a lot of use cases, creating one small object isn't going to make much difference, and you'd be right. However, if you look at how much can object creation hurt your performance, it really does add up. Um, so this is running a benchmark with 16 clients pumping events into the system and echoing them back and then waiting for them to return. And for each message that's sent out or sent back, one object is optionally created. How much difference does that one object make? Well, in terms of the average latency, it's around 170 nanoseconds. And if you remember from the previous benchmark, it was adding about 150 nanoseconds. So that they're in the right ballpark. But in terms of throughput, it's reduced the throughput by round about a third. Um, so it's a substantial reduction. Sorry, it's about a third. So it's a substantial reduction in the throughput you can achieve because of the impact of having all these threads trying to create our objects. One of the things to note is that in terms of different versions of JVMs, for this benchmark at least, we've got around 10%, little over 10% improvement from using Java 11 and above. In each case, these are completely default settings in terms of GCs, any kind of parameters. So there's no command line parameters being set. For the most part, I did play around with them, and it really didn't make much difference, which is to be expected because they're all very short-lived objects. The actual long-term memory that the application's using is very little. The time spent in a GC was around 0.3%. So it's a very small percentage of the time actually spent in GC. And this is not a third, it's actually a quarter, sorry. So it's a quarter slower. And the difference between the time spent in GC and the time spent, how much slower the system is a factor of 80. So the creating the objects is around about 80 times more expensive than the time it spends pausing to do GCs, which is a much higher margin than most people might expect because a lot of the focus is on the GCs but not on the allocations. When in fact the allocations, particularly if you're trying to use a lot of CPUs at once, could be much higher than the cost of the GCs. So how is there kind of some sort of, without further analysis and going through all this, um, how can I estimate how much impact I'm getting? Well, um, on a high-end machine, you can get around 15 gigabytes per second of allocations, depending on the size of the objects, as you saw previously. A typical quality enterprise server will get around 12 gigabytes per second. If you've got a second socket, it might be getting closer to 20, but sorry, second socket, second memory bank, separate NUMA region, etc. It's going to be around 18 to 20 gigabytes. High-end laptop, like the one I'm using at the moment, can get around 10 gigabytes per second. But you can see that the range in terms of what you can achieve on most systems doesn't actually vary as much as you might think for different specs of servers. So if you're going to be conservative, you would look at what fraction is your total allocation rate compared to 10 gigabytes a second. Now, one of the really important things to note from this is that this is for the whole system. This is not for a virtual machine. If you're running on a virtual machine with 4 cores, you might think, well, I'm fine. Actually, you're not, because it's what all of the um, processes across every virtual machine is doing, not just what your virtual machine is doing. There's no partitioning of this resource for virtual machines, or partitioning of the L3 cache or the memory bus. That is all shared. So if you've got even just one 4 CPU virtual machine running on a box and it's just allocating like mad, that will really slow down everything else that machine is doing, even though it's not triggering IO, and it won't necessarily show up in other ways, but the time it takes to allocate anything will be substantially slowed down. So you want to total up the allocation rate of every JVM across every virtual machine on that physical box. So if that totals up to be about 1 gigabyte per second, then you're looking at somewhere between 5 and 10% of the time spent is in allocations. And that may be quite reasonable, but it is good to have that ballpark figure. But if you're seeing that the total is getting close to 10 gigabytes per second, almost certainly you will get a performance benefit if you reduce your allocation rate and just not create so many objects. I have worked on projects where, excuse me, where the application was sitting at around 10 gigabytes per second when we did a saturation test. And then every time we reduced the allocations, what would happen is the allocation rate would just be the same. It didn't actually change the allocation rate. What would happen with the throughput would go up. So we reduced the allocation rate by about 10%, 10% less objects being created, and the throughput would just go up. The maximum throughput would go up by 10%, but the allocation rate stayed the same. And for one project, we didn't see a drop in allocation rate until we'd removed about 40% of all object creation. And only then did we start to see a dip in the allocation rate, not very much, and we saw nearly a 40% improvement in throughput as well. as a result. So that's without changing the code really substantially, just how we create objects or reducing the way objects are being created. Um, One of the biggest areas that comes up again and again from consulting arrangements is looking at the way you do logging, because logging is often your worst, biggest hitter from a performance point of view, but also from allocation point of view. So we've got engagement at the moment, and we put in sorts of monitoring and so on, but basically found that by and large, the way they were logging was in fact hurting them the most by far. There are a lot of other things they could improve, but so definitely have a look at the way you're doing logging is one of the first ways you might find that you can reduce your allocation rate and reduce the overhead of your application. A lot of applications we've worked on, it's around about 30% of the time is spent just logging. Um, and this is part of the reason why we don't do that, because we're using an event-driven system. We use Chronicle Queue, which is open source, and that basically the overhead is so much lower that it causes that problem to disappear. And because we record absolutely everything coming in and out, there isn't really any need to log anything unless something goes terribly wrong or we're on startup, for example. And so we produce almost no logs. And it's a lot of it's tied back to this, reducing the overhead, reducing the allocations, and also having a low latency messaging between processes, because the queue of one system can be read in real time by another. So it does tie back to this, um, but if for any system that you look at, I would suggest looking at the allocation rate and seeing whether you're probably saturating the system. Another alternative is you split the applications so that they're not together, um, or rearrange them so that all the critical applications have more than enough allocation rate. But obviously, if you can change the code so that it's not creating so many objects, that will almost certainly see a benefit. Um, so a related topic to this, which I have a whole talk on and a few posts on my blog, but I'll just introduce this, is that one of the things to look out for is accidental complexity. Accidental complexity is where your application is doing far more than it really needs to be doing, and that can be much more than you might imagine. We've seen examples where um, if you were to write it, and we've done this as a proof of concept, we write it doing only what it needs to do, the absolute minimum that it needs to do to meet all of its functional requirements, and compare it to the existing system, that can be 1 to 2 orders of magnitude faster, which means that around 99% of all the work it was doing didn't need to be done. It was entirely accidental, and it was all to do with um, uh, the way the application was doing it. That didn't. It was doing things that weren't functional requirements. And we have other examples where it was even higher, where you do it the same task, 2 different ways. Both of them complete the task as needed, and yet one of them is, say, 700 times slower to do exactly this. Well, it doesn't do all exactly the same thing, but it does. Both of them meet all the stated requirements. The one that takes a lot longer is entirely down to accidental complexity, and this is a big area for potentially reducing needless allocations, because if you can identify areas of accidental complexity and remove them, just don't do that basically, because they're not. Your application could be doing far more busy work that's not actually a requirement. It's not actually needed by the business than you might imagine, if you can do the analysis. And so yeah, something to watch out for reducing allocation rate. And so the key takeaways is if you're looking to use more than 4 cores at once, um, then looking at your overall allocation rate for the entire system, not just a virtual machine, not just a container, but the whole physical machine, um, could point to whether that reducing your allocation rate would really help the performance of the overall system, not just the JVM that you're tuning, but also all the other processes on that physical machine as well will also be improved by your busy or noisy application being optimized. Um, and Another thing to be aware of is that you can be in situations where the allocation are not the GC pauses. So you might look at the GC pauses and say, oh, it's spending 0.5% of the time or 1% of the time actually doing GC pauses. I don't see the point in optimizing the code because, it'll just pause it less often. That's no big deal. But what you're potentially ignoring is that the cost of the allocation that triggers those GC pauses is much, much higher. And so that's why looking at that as well, it can be very important. And last but not least is to say that be aware that this is a shared resource for your whole physical machine. So not it's not having containers doesn't create any isolation in this respect. It'll create isolation for the CPUs, but the contended resource here is not the CPUs; it's the memory subsystem. Okay, so that's quite a short talk. Um, I'll open it up to questions. It can be about this, or it can be about low latency coding in general, or any other topics that you're interested in.
All right, thank you, Peter. So we have a couple of questions. One is from me, and the other one is this one from Andre. How to test or calculate the max allocation rate on the host? I think you partially answered it, but is there like a mm,
It,
preciser way of doing it?
the best way, well, it will depend on, as you saw previously, it will depend on the object allocation size. So the size of the objects you're allocating um, within bounds. The simplest thing is to run a saturation test. So run a load test where you're pushing through as much data as possible on the system, and then you can do this with a single JVM. You don't need to have multiple JVMs to test this. So that way, that single JVM, or maybe two if you've got a load generator and another one, um, and just add up the allocation rate you can achieve between them. Now, it is possible, obviously, that your application isn't just allocating, right? So it's doing other work and so on, and the bottleneck may be somewhere else. But that's kind of a good sign, because if the bottleneck's somewhere else, then allocations aren't actually your problem. But if your CPUs are being maxed out by this, and you're not just waiting for a database or some other external resource, or it's just doing disk I/O all the time, then that will show you what your allocation rate is for that machine, and then you can see where that and certainly have a look at the ballpark. Is it somewhere around 10 gigabytes or more? If it's nowhere near that, then I would actually suspect you're actually CPU bound. So it's not actually your allocations that's slowing you down.
Okay, so I would add to that I was recently quite impressed by the ZGC garbage collector reports about the statistics. It actually does report the allocation rate across GC cycles, and it's quite interesting because you can get like a very precise number directly from the garbage collector that says, hey, in this, between these two pauses, or depending on the frequency of the statistics that you want to print, you can have a total numbers printed out, so you have a
That's
live number in that sense. But yeah,
that's well
it's
worth measuring.
yeah,
Yeah, you would just want to have some way of collating that if you've got multiple
yeah,
JVMs on the same machine.
yeah, and
But
so
yeah, definitely worth watching out for. Um, although it's not something that should vary too much. You've generally find that I mean, your workload might vary, but for the most part, the systems I've seen, it is pretty much the same over long periods of time. It doesn't actually go up or down that much. So if you can even just do a sample on a test system, or see how it goes in production for a few hours, on like your busiest hour of the week is usually a good place to
Yeah.
start. And yeah, that'll be enough. You don't have to like watch it all the time.
So we come back to this other question from Mark, which asks, what are the tools that you can use to measure your machine's allocation rate? So we just talked about this. So it's basically, if I understand you correctly, it's basically like a synthetic test to measure the maximum allocation rate that a JVM can actually sustain on that particular hardware. And so that's your so it's not the baseline is the top line I would say, and then you can benchmark your own application and see maybe through the garbage collector logs or something.
Yeah, if testing your application isn't really practical, I mean, the very first benchmark I used just used an in stream of 0 to n threads where in parallel it was generating lots and lots of objects. So you can do it with a very short piece of code. The problem is then you sort of do need to know roughly what sort of size object you're testing for, but that has the benefit that it's completely self-contained. You know, it's just maxing out on allocations, and yeah, you can see what it's doing. So I would probably do that for comparison anyway, just as another data point to understand your system.
Yep. We got here another question which from Hemal Daha. We'll see. Haven't used Chronicle Queue, but having another service running in the same node or the VM versus log IO, how is the comparison results you've got? So I think
Yeah,
you
sorry, go on.
hinted in your presentation about moving the logging through Chronicle Queue and versus the typical logging library to go through an appender on the file system. So did you have any comparison numbers about these two styles?
Yeah, so one of the things that's important to note about Chronicle Q is it's brokerless. It entirely uses shared memory in the kernel, so managed by the kernel. So as long as the kernel's running, you're good. The data will get written to disk. The process can die immediately, and that data isn't lost as long as the system runs long enough to flush it to disk. So there's no broker involved. There's no TCP involved. It's entirely through shared memory, and that's how we can get the low latencies between JVMs going via Chronicle queues. So a typical latency is somewhere around 1 to 3 microseconds. That includes serialization and deserialization, as in a delay between processes. Obviously, in benchmarks, we can get well below a microsecond. For larger messages, it can be up to 10 microseconds, but that's the sort of time frame we're talking about. This is much lower than TCP can achieve over loopback, for example, and it's persisting, right? So everything is written because it's written to shared memory and to memory map files. All of that data is will be flushed to disk by the operating system asynchronously. You can add synchronous writes as well, but obviously that slows things down. But if that's what you need, you just have to pay that penalty. Um, Although what we actually encourage you to do is synchronize based on business requirements. So most broker systems, what they'll do is they'll synchronize every n messages or every n megabytes, but that doesn't represent business value. Right? It doesn't represent, well, actually, how much money could I lose if that data was lost, for example. So what we actually encourage people to do is say, well, let's say you've got a payment or an order for $10. Maybe that's acceptable to lose, but one comes in for 1 million. You want to stop the whole system and wait until it's written to disk. So just basically inspect the message, see whether you've either accumulated too much risk or that message has too much risk, and then you sync that message. But then basically you do it intelligently based on business requirements rather than just some sort of technical metric. Um, so in terms of compared to I/O, it is actually writing to memory map files, and those memory map files can be shared between Docker containers, for example. So we can get, 1 to 3 microsecond latencies between Docker containers as long as it's on the same physical machine. Um, and Yeah, so that's a lot of the reason why we go down the road, because a lot of it's about low latency as well. Because you're copying everything synchronously, there's no need to allocate things. There's no need to double copy things so that you can pass it off to another thread to write it to I/O, because as soon as the I/O is returned, a copy has been taken and put into the memory map file. So you can now mutate it. So you don't need to. It reduces things like defensive copies and stuff like that.
And so, if I understand correctly, this is mostly used as a log for transaction log of operations that your application might do. Have you ever used this? Or I'll make the dumb question here. For example, do you have any or someone crazy that has done a SLF4J binding onto
Yes,
Chronicle
we have.
queue?
Yeah,
You
so
did.
we have a library called Chronicle Logger that has SLF4J bindings, and it has log4j, log4j2, and it has a few of the
Oh,
loggers
okay.
bindings there. Um, that gives you a lot of the benefit, but it has a couple of downsides. One is that the API itself has a certain amount of overhead. So generating the message, using the formatting, all that string handling, that's still there because that's all before the appender is actually called.
Cold.
Like, so what we tend to do is we don't do any of that. We just write straight out to the queue. But in terms of migrating, if you're looking for a low code change drop in, then that'll be the approach you use. And in fact, for one of our clients, we're looking for some sort of fairly quick fix for them, and that's what we're looking to do is to drop in Chronicle Logger in their case. It's not just a transaction log, it is also a messaging system in that messages can be read in real time as they're written as well. So that's actually the most common use case. The simplest use case is just a log, a replacement for logging. But in general, it's used as a communication between microservices,
Yeah.
which is persisted, of course, as well.
Yep. And I imagine the receiver of these messages has to poll, or is there like a notification mechanism which,
No, it has to busy poll,
okay. Yeah,
which
makes
works
sense.
well in some cases, but it's not always desirable. We have some back off strategies so that you're not necessarily burning CPU if that's
Yep.
not appropriate for your use case.
Yeah, yeah.
Um,
Okay, and let's see. I have a question. You mentioned about techniques that you've been helping clients with to reduce allocation. Can you expand on that? What techniques, especially you were using, or if it's just like code review and don't do this, don't do that.
yeah, it's certainly cutting out things that don't need doing. So one of the ones that is very expensive is, again, to do with logging, is if you include the caller's class and method name. So it's very helpful to add. It's very useful, but it has the downside of being very expensive because it goes and creates a stack trace for the whole thread. For some JVMs, it causes the whole JVM to stop, every thread in the JVM to stop so that it can take that stack trace. Then it creates all these objects. Like, it's not just the one that you're interested in, it's creating a row for every element in the stack trace. If you've got a fairly deep stack, that can be 100 or more times about 6 objects or something. A lot of them are strings. The strings themselves, of course, have got underlying arrays, right? So just to get out maybe 2 words, which is your class name and method name, you've created far more objects than you might imagine. And this is just down to configuration. So while it is very useful, That can be an immediate example of just from configuration alone. One of the things we do is we do store mutable objects in thread locals, but that's kind of as a last resort if there really isn't some other way of just eliminating it entirely. So you could have like a string builder that's in a thread local, you clear it and then reuse it. Um, but it's a case by case basis as to whether that's really going to help or not.
Yeah.
Um, and I would only do it where it's very hot in terms of object creation. Um, Earlier versions of Java had the problem that if you were to append an integer or a double, for example, it would first convert it into a string and then append the string. Newer versions of Java don't do that. They will write it straight out to the string builder. So certainly Java 11 plus does a better job of removing allocations for you, just both in the libraries and to some degree with escape analysis as well.
Yeah.
So I would go back to the profile at this point and say, well, where's my biggest object allocation? Do I really need to be doing that as often as I am? And is there another way of doing this without creating objects? And also just changing expectations. People just expect applications to just generate a lot of garbage all the time continuously because that's all they've ever seen. But in reality, that doesn't have to be the case. For many years, I've worked on applications where the Eden size was larger than the amount of garbage it produced in a day. So literally over a day, you would just slowly see the Eden fill up. So there's no minor collections, no major collections. And
Yeah.
then once a day, it triggers a full GC as a maintenance task overnight during a maintenance window. It's a maintenance window event.
Exactly.
And
Half an hour before the opening.
for example, yeah. So that way, how you've configured the GC at this point doesn't really matter too much
Yeah.
because it doesn't run unless something goes wrong. I have seen it run during the day because it was spewing exceptions, for example, but due to some problem. But nevertheless, so it is still useful. I wouldn't just turn it off, right?
Yeah.
But it's more like when I start up a lot of our applications, I'll put GC logging on just to see if it GCs at all, right? And if it GCs at all, then that's a problem, right? So I expect that log to be very short,
Yeah.
but nevertheless, it's you don't need to go to that extreme, but it's useful to know that you can go to that extreme if you're willing to put in the development effort. And like I said, it's often not worth putting that much development effort in. But there is a middle ground, right? There's a middle ground between creating objects just like mad and just recoding everything so that it don't produce any objects hardly. So um, you just
Absolutely.
find the point where it no longer matters how much you're allocating.
Yeah, yeah. Absolutely. In the development of Jetty, we are facing this and we're trying to be really cheap on allocation, even though it's really difficult. And oftentimes we find ourselves into maybe a small piece of code which is maybe not the hottest one, but a good one, a good hot one, and then finding ourselves to go from using JDK 8 streams back to for loops just because of the allocations that, if you have to do, 3, 4 filters and
Mm.
maybe a couple of mappings, and then, every single time you do one of such operation, you allocate another stage of the stream processing, and it's allocation. And if you do it the old way, you just store that information into mutable variables, and
That's right.
it's
Yeah,
okay.
but that's where using a profiler really helps because
Yeah.
you can up to a point it does a really good job at optimizing streams.
Yeah.
So you can find that actually a stream that looks like at first glance like it must be creating all sorts of objects, but actually it doesn't create any at all. But then if you've got a capturing lambda, that usually what triggers, catches people up. I think, oh, this is not actually creating an object here, but you're referencing something else. Now it's a capturing lambda. Now it needs to create an object to capture that value. And hey, every iteration or every usage, you're creating an object.
Yeah, yeah. And so I'm actually curious, and I'm trying to push you on a on object pooling. Are you doing that in some kind of form or
Yeah,
another? Because
we
there's this old saying that, oh, object pooling is bad because it's going to interact badly with the garbage collector. Everything ends up into old generation. It's more costly, blah blah.
mm.
But you allocate less.
Yeah, so one of the biggest problems with object allocation is that objects, as we saw earlier, creating objects is so cheap, right? So if you're not careful, your object pool will be far more expensive than just creating a new object, like far more expensive if you're not careful. So say for example, I'll use a hash map. Well, straight away your entry is going to create an object, and then before you know it, you're having to do a hash of something quite expensive, and the whole thing. Um, your object pooling. It's not like object pooling connections, for example.
Yes.
Connections are so expensive that it just makes sense to pool them. But if you're just pooling objects, unless you're very careful, it can end up costing you far more than it's worth. So I do actually have an object pool, which I'm quite proud of because it's quite odd in the sense that it is shareable, so it can be shared between threads, but it has no explicit thread safety guarantees. And the way it works is that it doesn't require anything more than what the language implicitly guarantees, like final fields are set in constructors, etc. So it can be shared across threads without any locking, without any explicit memory barriers. Um, and so it is extremely lightweight and does a very good job at caching. So we use this for all our deserialization of strings. If they're not put into something mutable, then it will use this object pool. But it's relatively rare that it it's really worth creating an object pool. Um, Another way we avoid it is that we will use longs. So we have a number of different kinds of encoding. So we use longs for timestamps, date time, nanosecond resolution timestamps. We use longs for short strings. And so when it comes out in text, when it's read in text, it's encoded and decoded for you. But internally, it's a long. So it's passed around as a long. Then it's just a primitive. There's no object allocation. The overhead memory access overhead is much cleaner. And so that's another way we deal with it. We just turn short strings or timestamps into longs.
Yeah, yeah, up to 8 characters. If they're ASCII, they can fit into a long. So, yep.
Yeah, or you can go to, if it's base 85, and there really is a thing
Ah,
called base 85, you can get 10 characters into a long.
right, right. Yeah, yeah. Okay, so we have a couple of other questions. This one is interesting. How much do you desire for value objects in Java?
Um, yeah, good question. The reason this is good is because we do implicit recycling of objects ourselves when we're reading from queue. So we heavily rely on mutable objects. Um, but we do very much use DTOs very much. A lot of data-driven tests, um, clear separation between data and business logic. So we do like that approach, and all of our microservices are fundamentally single-threaded as well. So we don't have to share data between threads explicitly. Implicitly. We don't. We use the shared memory queues, but we don't actually share within a JVM data between threads as such. So we kind of use a different model, which so like for example for Project Loom, it makes creating lots of threads, virtual threads, much easier. But we tend to go the other way and say, well, each microservice has a dedicated, isolated CPU, and that CPU will not run anything else by design, right? And so it's down to how many cores you've got. That's how many critical threads you're going to have. So it's a very different approach. It's kind of almost in the opposite direction.
Yep, very interesting. So yeah, value objects, if I understand it, they will be mutable. Records is the same, and so
Mm.
yeah, it's a different part of how you can use the Java language. It's quite amazing how many choices you have. So it's really
Yeah,
good.
we encourage the simpler setters. So we don't use set and get. We just put the field names, a bit like C# does.
Yep.
So yeah, we do like that sort of thing. It's how we approach it, and we have a superclass that im implements things like equals and toString and hash code for you, and does it using generated code. So it's all very efficient. So,
Yep.
but obviously things like values will do that for you without having to create some magic in the background, which will be much nicer.
So related to the allocation, we go back to Andri, and can JDK Lilliput improve scalability because of smaller object footprint?
Yes, a smaller object footprint. So the smaller the it's there is an overhead per object overhead, but it's also just a sheer bandwidth problem as well. So making objects more compact will not only make allocations more efficient, but also scanning, reading objects or updating existing objects. More of them will fit in your L2 cache, more of them fit within in your L3 cache. But the key one is the L2 cache, because even though computers are getting bigger, you're getting more memory, you're getting more disk space, you can get, I mean, there's the next generation of micro SDs will be 2 terabytes, which is enormous. But your L2 cache is only a quarter of a megabyte. So if you want all your cores to run independently without getting in each other's way, you want your application code and data to fit within a quarter of a megabyte. And then they won't talk to each other. They won't get in, and then they all will run completely independently and efficiently. So anything you can do to make those objects smaller really does save up when you're thinking about, well, I'm squeezing each one of my threads into a quarter of a megabyte, ideally.
Yeah.
Obviously, in Java, you don't have real control over this, but this is sort of like a just a general sense, really, rather than um, a something you can control, say, like in C++ or something.
Yeah. Yeah, and the chances that you need to, this extra, you lose a little bit of features, let's call them this way, when you go Lilliput, because you probably lose the storage of the identity hash code and stuff. But they are quite rare, and the bias locking too. So I think it's gonna be some other big improvement performance-wise that you update, like you said before, you update from 8 to 11 to 17, and magically the system goes faster, and you say, "Oh wow, thank you."
Yes.
That's really nice. And so this one will be probably another big one with respect to performance. So I think we answered pretty much all the questions that popped up in the meanwhile. So, yep, I think so.
Very good.
So I think we can wrap this up. Well, thank you very much, Peter, for the session and your experience and the answers and everything. So, well, I would say enjoy the rest of the J Champions conference and see you soon, hopefully, at some
Yes, in
conference.
person.
Yeah,
Yes.
in person.
Looking forward to
Thank
it.
you.
Thank you, everyone. Have a good
Bye,
evening.
everyone.